My name is Tanya Akumu, and I'm a research engineer from IBM Research in Africa. And today I will be talking to you about anomalous subsets. But before I start, I'm representing my team. I work with an amazing team from across the world, and we work in the Nairobi lab. So here's my outline for today. I'll be walking you through the motivation and approach, and I'm really excited about getting our hands on some code at the demo stage. So why do anomalous subsets matter? As data scientists, we want to understand data at a subset level, but that may look like cherry picking or data dredging. What we want to do is to bring discipline and scalability to exploratory data analysis. Two application areas of better anomalous subset understanding are in bias detection and detecting concept drift. But before we get to bias, I want to talk to you about a much simpler type of analysis, which we call stratification. Stratifying an outcome of interest is one of the oldest forms of analyzing data, and here are two extremely simple examples. On the left, we see child mortality varying by age in Nigeria, and child mortality varied by region, and then on the right, we see student loans varied by age. And yes, I am one of the 26% under 30-year-olds who still have a student loan to pay back. So stratification is useful because we know the mean of an outcome doesn't tell the whole story. In other words, when we know the mean, it doesn't tell us the distribution of an outcome over different subsets. Stratification is a manual attempt to find subsets where the outcome is much higher or much lower than expected. For example, on the left, the under 5 child mortality rate in the Northwest region is much higher than the national average. So I've told you that stratification is one of the oldest ways of analyzing subsets of data. However, it's still being used today because it has a lot of things going for it, such as it being easy to interpret and communicate to non-technical people, like your manager maybe. But it has some cons, such as it being limited to 1 or 2 features at a time, and relying so much on human intuition as to which choice of feature to stratify across. Subset scanning allows this stratification to be done in a more disciplined and scalable fashion. So the takeaway from motivation is that subset scanning allows stratification to be done in a more disciplined and scalable fashion. And now on to approach. And there are 2 things that I want us to understand. One is how we score the anomalousness of a subset, and 2 is which subsets we consider. So first off, scoring functions. At the bottom of this slide, we have a likelihood ratio based off the Bernoulli distribution. However, this provides no intuition as what it means to be anomalous. So let's consider a toy example based off my adorable puppy, such a cutie. So say we have customer records from a pet store, and from these records, 40% own a dog. So this is what we would term as mean outcome. Then we consider 2 subsets: customers living in the suburb areas and customers living at the beach. Dog ownership increases to 50% among suburban houses and 75% among beach houses. However, there are 20 times more suburban houses than beach houses. Which of these 2 subsets are anomalous? Okay, so I sort of tricked you. The most anomalous subset is actually when you consider suburb and beach houses together, as we see on the right. This simple example is to emphasize that our search space is not just individual feature-based, but rather groups of feature values. Scanning approaches don't just score individual feature values like suburb houses by themselves or beach houses by themselves. We also consider subsets of feature values such as suburb or beach house together. It is possible that groups formed this way are more anomalous than scoring records from individual feature values. As you can see, the score of 21 is much higher, is larger than 16 and 10. And so we can conclude that dog ownership deviates further from what we expect, that is the 40%, when considering suburb or beach houses together as compared to their deviation from the mean when considered individually. So up to this point, you should understand that scanning is trying to maximize a scoring function over groups of feature values like house type, and it's possible that combining house type results in a higher subset. This approach only works if there is only 3 or 4 house types, but it quickly becomes intractable as the number of possible house type increases, and we cannot naively score all combinations of subsets. So how do we handle the exponentially many subsets? The answer comes from mathematical properties of the scoring functions, which we call linear time subset scanning, or LTSS. It turns out that we only need to consider linearly many subsets and not exponentially many subsets, while still maximizing the scoring functions over the entire search space. So although details of this property are outside the scope of this talk, the intuition is that the vast majority of subsets are provably suboptimal and cannot be the highest scoring ones, so we just ignore them. It's pretty cool, right? But I need to make one more comment before we get to examples and code. So recall, I had mentioned an application that subset scanning was detecting predictive bias in machine learning models. However, all I've talked about is finding subsets that deviate from the mean. So where's the predictive bias? Let's return to our example in Nigeria and again consider a predictive model that assigns everyone in Nigeria the same risk of child mortality rate, the national average of 13%. So this model would be over-risking children in the southwest region and under-risking children in the northwest region. The model is consistently making mistakes against some subgroups of records, and we want to find these anomalous subgroups. That is what we call detecting predictive bias. So we're not saying that using the outcome mean as a predictor is a good model. Our focus in this line of work isn't the predictive model, but rather how we can inspect it for bias. Inspecting the mean model, bias may sound a little bit odd, but it's why people stratify an outcome across features and compare it back to the expected mean. So this interpretation of stratification and predictive bias begs an obvious question. Do we have to use the mean of an outcome in a data set as expectation, or can we use something else? Well, the mean can be replaced by any predictive model you want. The scanning algorithm doesn't change whether the expectations come from a mean or a complicated network model. We are still maximizing the scoring function of a very large search space in search for subsets that are deviating from what we are expecting. And now I want to go through 2 different examples that we've applied scanning on. The first one will be scanning over anomalous subsets that deviate from the mean, which is what we've termed as stratifying of an outcome. And the second example will be scanning for anomalous subsets that deviate from predictions made by a simple machine learning predictor. So the first example is the work that we did with the Gates Foundation to study neonatal maternal maternal newborn health in Ghana. We were given data from a study that collected details on pregnant mothers and their births, and the features were like age, birth weight, and education. And in this study, we wanted to better understand neonatal mortality events for about 20,000 records. Unfortunately, 1.5% of the bats in this study resulted in a neonatal mortality event, and this is what forms our outcome of interest. Could we find a group of bats where mortality events are highest? And remember, the problem with treating this as a search problem is that there's 4 trillion subsets. There were 4 trillion subsets to consider in this data set alone. So what did scanning find? We found a subset of bats in the circumstances where it was a home delivery attended by a medical profession. Under these circumstances, 42% resulted in neonatal mortality event. Recall, our expectation was 1.5%, so this was an extremely anomalous subset. In fact, nearly half of all the deaths in the data set occurred under this situation, and the client was unaware of this pattern, and we were able to have an interesting dialogue on how data was collected and correlation versus causation. The second example is how we've used scanning to look at COVID deaths from a large data set in the US. We didn't use all the records, but rather focused on only hospitalized patients. We trained a simple logistic regression model to predict mortality based on about 30 to 40 features in the data. However, our goal was not to train another predictor model. I mean, anyone can do that. But rather, we wanted to better understand what subset of patients did the model consistently get wrong. Again, predictive bias. The scanning over billions and billions of subsets, we found an anomalous subgroup were of cancer patients under the age of 50. It was a relatively small subset, but it was highly anomalous because of how far the model predictions were for this group. Our model expected 80 deaths in this group, but in reality, there are over twice as many. And this bias suggests that there's a fundamental interaction between age, cancer, and mortality that the logistic regression failed to cover. And now for the exciting part. We have open source the scanning algorithm in IBM's AI Fairness 360 toolkit, and you can access the code if you want to run live with me through the QR code, and there's the GitHub link over there. So there's a notebook that implements this scanning algorithm. And we'll start with importing our libraries. We're going to use the AF360 MDSS detector, which is where the scanning algorithm is. And then we'll use matplotlib and numpy to interpret our results. So we run that, and then we load our data. This data, we're going to use the 2014 data and 2018 data on US income data records. We got this data from the Python package fork tables, and it's about 1.6 million records for the whole data set. But for the sake of this demo, we'll just use 100. We'll just sample 100,000 of those. So we load our data and check that it's loaded correctly. And then these are just some helper functions to help interpret our results. So then we're going to set up the MDSS API, that's the BiasScan API, and the parameters include the scoring parameter, which is what we use to specify the scoring function to use. And then we have a predicted parameter, which tells us which direction we want to scan. Do we want to scan a subgroup that the model favors or disfavors? If we set it to true, we scan a subgroup whose predictions are favorable compared to what we observe, and if it's false, that's the vice versa. Then we have the penalty coefficient, which we use to adjust the complexity of the highest scoring subset. And this complexity is in terms of the length of the description. So we extract our features and we extract our observed outcomes. Then we call the bias scan object and pass it the features observed. We set our scoring functions to Bernoulli because this is a binary classification task, and we assume that the distribution is Bernoulli. And then we set ever predicted to false, and we give it a penalty of 5. So we run that, we run the scan, and then we visualize the subset that is returned. So that takes a few seconds. As you can see here, this is the anomalous subset returned. People that are over the age of 30 to 70 and have a bachelor's degree or higher, or work more than 30 hours a week and are married or have a partner. For this specific subgroup, the probability of earning greater than 50,000 is 0.73. But our expected, that is the mean, our mean of outcome was 0.3. So you can see there's quite a big deviation there. Then we can also look for groups where majority of them are earning less than 50K than what we expect. And so the only change that we'll do is we'll set the overpredicted to true. And again, we find a subgroup of people between over 20 years, between their teenage years and over 20 years old, but have a school level of bachelor's degree or lower. They have a probability of 4.9%. Like 0.04, which is much lower than what we expect of 0.3. And then recall, I talked to you about the penalty value being a coefficient that affects the complexity of our subset. Earlier, we used a penalty value of 10. So if we reduce that penalty value, we end up having a very long subset. And the complexity here is what we call the length of the description of the subset is what you can penalize using the penalty coefficient. Right. So then now I'm going to walk you through an example of bias scan. And we're going to use an X-ray classifier and the AUC score to evaluate our model. So in this case, we want to find the concept drift. We have data from 2014 and we have data from 2018. We want to train a model on 2014 data and then use this model to predict the situation in 2014 and then compare that with the actual situation. So we, again, load the data, separate the features and the target, and then we train our model, and then we run the scan. So training a model might take a little bit of while, so a little bit of time. So we get our model results. We can see in 2014, the model performance has a very high AUC score, but then in 2018, that score, the model performance has reduced, which is what we expect. But do we know, then we scan for subsets comparing the situation with 2018. So we have our predictions from the model. The model predicted the situation in 2018. And then when we are setting the bias scan, we now pass in our expectations as these predictions from the model. So there's the expectations parameter, which takes in the predictions, and then we still specify our scoring function as Bernoulli. We get a very high anomalous subset of occupation, a number of occupations that majority of them ended up earning higher results. So we compare this subset with the 2014 and what the model predicted. So in 2014, for this anomalous subgroup, the model predicted that 22,000, around 23,000 people in this subset earn 50K and above. But in reality, that was 23,000. So you see, it's very close. The model was close in getting it right. But then in 2018, the model predicted that 26,000 would earn greater than 50K, but in reality, this amount like in reality, the amount was quite low. That is 36, actually it was quite high, 36,000 and this amount. So that ends my demo. And thank you for listening to the talk. These are my contacts. Again, if you'd like to access the code, it's right there. And I invite you to ask any questions you may have. Thank you.
I have a question from Shannon. I really loved your talk. One question though, in terms of replacing the mean with an ML model, I'm assuming this introduces a new set of errors. Does it propagate across subsets differently? How do you account for or correct?
It doesn't, I'm not sure where the errors come from exactly, but the model just gives us the only difference between using a model and using the mean is that each record has its own probability from the model compared to each record being assigned the mean. So the scanning algorithm is not affected by the different probability distribution. It will still find the anomalous subset. So there's no errors that are introduced in the scanning itself because it uses the probabilities that it's given.
Another, David, very cool method. Can you say a little more about other applications? I know Celia et al. Did some work using it to look for adversarial examples, and I could using text domain shift where the distribution of data changes, similar to the concept shift example.
Yeah, as you've said, we have applied this scanning in detecting adversarial attacks. We're also looking to apply to new data sets and new domains, which is where you guys come in, because most of you are in diverse backgrounds, and we would like you to apply this tool and let us know if you find some interesting results. Yeah, we're still continuing to use this application. I think right now we are doing some work with an NIH grant with a tech hub in Africa called Madiva, where they're looking for multimorbidities in diseases, and they have a ton of data, and we are using this scanning algorithm to help understand the patterns that are there.
Follow up from David. Are there methods for tuning the hyperparameter you mentioned?
Yeah, so it's actually mostly it depends on the data set that you have. If you have domain knowledge, so for example, you know some features are not relevant to the outcome of interest, or or if you have some features that have a high number of unique values. So as you saw for the occupations, we have very many types of occupations, and perhaps that doesn't really inform our outcome that much, then you can use the penalty value to limit the number of, not the number of features, but like the length of the subset that is returned. So it actually just depends on your data and the number of unique values for each features and what you're looking for.